Hello, everyone. My name is Vijay Samuel, and I'm a principal architect at eBay.
I'm Tang from eBay Observability Platform team. Nice to meet you.
And we are here to talk about our journey with the OpenTelemetry, specifically using the SDKs and collector for tracing and how we derived some interesting configurations for the pipeline and what are the conclusions that we could make out of it. So today we'll talk about introduce tracing in general. How does tracing in eBay look like? What are the problems that we faced? How we went about solving them? Some lessons we learned along the way, and if time permits, we'll take some questions towards the end. So the OpenTelemetry website or the documentation basically describes traces as a means for us to get the big picture of what happens when a request is made to the application, whether your application is a monolith with a single database or a sophisticated mesh of services. Traces are essential to understanding the full path a request takes in your application. So I'm just quoting as is from their documentation on this. With regards to our scale, we offer 14-day retention, which translates to 190 billion spans per day or 2.2 million per second. For this, we use 3,600 provisioned CPUs and 150 terabytes of storage. It does not look like a lot, but and the reason for that is that we trim it down to a great degree to the point that we actually find use without excessive wastage. From an architecture perspective, we have a bunch of Kubernetes clusters that all the eBay applications, both internal and external, run. We have 3 classes of applications that are there. 2 of them are managed for Java and Node.js, which just means that there's an SDK that our platform team provides, which has everything that you need to develop and deploy an eBay application that serves our customers, or generic applications which are you like Rust or you like Go, write your own application on top of that, or off-the-shelf open source that you're deploying inside the company. So with OpenTelemetry, all of these can use a standard SDK. For the managed, we have a wrapped SDK, which does some free instrumentation. All of them write to OpenTelemetry collectors. And basically, they go into a tracing gateway where the raw traces, sample traces are written. Similarly, we have a metric ingest where all the Prometheus endpoints are scraped for metrics, written into our metric store. And then we have our console where you can visualize. There's a tracing query which talks to the trace store, a metrics query that talks to the metric store. This is typically how people observe inside the company. So what's the problem? Tracing in general is hard. Tracing can become grossly expensive depending on how much metadata you're stuffing into each span, how many span events you're doing. If you're doing 100% sampling, that's a very large scale that you need to go after. And before the open tracing, open census, OpenTelemetry came about, we had our own tracing-like logging platform, which when we do 100% without repetitive metadata, still has a 15 petabyte a day worth of scale, which is a lot. There's a high barrier of entry for the end user because you need to make sure that every layer in your call chain has tracing instrumentation done with proper context propagation, and this just results in too many moving parts. So if your call chain has 100 microservices that are involved, which is very normal in our use case, even if one is instrumented incorrectly, it leads to a call chain that's not accurate, and if you are troubleshooting an incident, it can lead you into a wild goose chase. OpenTelemetry isn't easy either, specifically for tracing. So there is this common Lego analogy that people use for the OpenTelemetry collector. There are many building blocks with different kinds of receivers, processors, exporters. There are many ways to piece them, and depending on how you create the the pipeline, you either create something that's really beautiful or you basically create a monstrosity. So you can do one tier of collectors, you can do two tier, you can do more tiers. Common questions are, okay, Kubernetes enrichment, do you put it in the first tier, second tier, which stage of the first tier it should be, so many questions. And from an adoption perspective, specifically for tracing, there aren't too many installations for which we have case studies that have been done to say that this is how tracing looks like. But metrics, on the other hand, more people have talked about it over the years, a little easier to go after. But the OpenTelemetry community is extremely vibrant. Lot of information is being shared out. But at the same time, like, if you don't keep up, you're going to miss out, because it's one of the more rapidly evolving communities that are there today. Along this journey, we tried several things, but they never stuck. So let's go one by one. We first tried a single tier of collectors where your applications can write to an OpenTelemetry, a fleet of OpenTelemetry collectors, where you first do the K8s enrichment, followed by span metrics processor, which can generate the red metrics, followed by tail sampling, after which you write the traces into the trace store and the metrics into the metric store. Subsequently, what we tried to break it out a bit in a two-tier approach, where application writes to the first tier of OpenTelemetry collectors, where we have first the K8s enrichment, followed by the span metrics processor. The metrics get written into the metric store. We have a second tier onto which you pass the traces, and you dual write the raw traces into the trace ingest, so that when it lands in the trace store, you have you have two sets of traces, one which is raw, one which is sampled. And if they sit on two different tables, you can have different retention policies across the raw and the sampled. And we did another iteration of the two-tier, where applications write into tier 1, where there is just Kubernetes enrichment. On the first, second tier, you have the span metrics processor, where you create all the metrics and write them into the metric store. The other second tier has the tail sampling processor, which writes sample traces into the trace store, but you also have a raw feed from tier 1, which writes the raw traces, and the same methodology, different retention for two different tables. So we, at least until the previous iteration, we randomly tried different things which did not stick. And so we went into a more structured methodology, where we wanted to solve different kinds of problems pertaining to tracing. And some of them are, we wanted to solve for mass adoption. We have roughly, I want to say, 8,000 odd applications inside the company. Going after each one of them to do instrumentation is near impossible. We wanted to tune the pipeline, which we just talked about, to make sure that we are squeezing as much performance as we can out of it. Scale the whole platform in general, not just the OpenTelemetry collectors. Make sure that we are having the right storage methodology and doing sampling the right way. So let's talk about mass adoption first. The thing that we wanted to go after is identify the highest common denominator. Like I said, the managed framework-based applications, they constitute 90% of the site, which means that on that SDK, if we have some instrumentation that's being shipped out, it would more or less cover 90% of the site. And this framework has a concept of a mandatory monthly site-wide upgrade. So there are automated pipelines that can basically refresh all the components that are part of the managed SDK, and they automatically get rolled out into all of these 8,000 applications every month. So this allows us to provide out-of-the-box tracing without the end user having to lift a finger. The next part would be to go after the service mesh. We are adopting a service mesh inside the company, which means that for all the applications that don't belong to this managed stack ecosystem, as long as they are on the mesh, the spans that are being generated by the mesh itself using the OpenTelemetry SDKs and whatnot, that would cover the remainder. And we really want it to be in a place where instrumentation is optional for the end user with regards to tracing. They can do more custom spans that they want to, but all the basic interactions like serving an API or making a client call or making a database call, they are all offered for free without the end user having to do much. So from the managed stack perspective, we ship the OpenTelemetry SDK, and we have free instrumentation for client calls, server APIs, database calls. For some, we are actively covering as many as we can. We also have it for our devices, iOS now, and in the near future, we'll do Android as well, and maybe browser in the future as well. And all these SDKs, they sample at 2% by default. And that's the tracing side of the managed framework. And on the metric side of the managed framework, we also ship all the 4 golden signals for free. And on the latency metrics, we ship what are called exemplars. Exemplars denote a point-in-time value for the metric that's being considered. So, and these exemplars have a trace ID and span ID that are embedded into them, which means that when you have an alert, you can look at a metric, and the metric will have a sample trace ID for which you can look at the trace, and from there, in turn, you can jump to either the logs or a profile, and we like to call this the 3-click RCA. Along with this, since we use the span metric processor, for every span that's being shipped into the platform, we also have the red metrics that are being automatically computed for every span. The next part is pipeline performance tuning. When it comes to performance tuning, numbers are everything. So we started breaking down the pipeline and assessing the throughput component by component. For every permutation, we basically looked at the numbers and kept moving on to find out which would be the more optimal way to piece the Legos together.
Can you guys hear me? Hello? Okay. So in the beginning, we only have one simple pipeline, and spans flows from left to right and save to our backend. Then we want to get metrics from spans, so we add span metrics processor in the pipeline. We also need to get the pole metadata as span attributes and metrics labels, so we add K8 as processor before it. And as the traffic grows, we need to add more pods. Each pod will run the whole pipeline. And we found it is not scalable. The reason is K8 as processor, it actually needs almost a fixed size memory to hold all metadata for one cluster. So no matter how many pods you are running, each pod will need a big chunk of memory to do that. So we turn this pipeline to 2 tiers. The first tier runs K8 as processor, and it has few pods, like 3 to 5 pods. But each pod has high memory, like 10 gigabyte to 20 gigabyte, so that it can hold all pod metadata for that cluster. And the second tier runs span metrics processor. It has more pods, but it only has like 2 gigabyte. When we have more traffic, normally the first tier stays the same. And we need to scale up the second tier because span metrics processor will need more memory to hold labels. That's how we solve the scale of this pipeline. So we enable auto scale. This feature allows us to handle seasonal traffic very well. We can scale down when have lower traffic. We can also scale up when we have higher traffic. This allows us to save lots of resources. And we also met some problems like the OOM issue when using the service object. It just cannot handle gRPC traffic quite well. So we moved to Envoy and service mesh to get more balanced traffic in the pipeline. We use ClickHouse as our backend storage. Jaeger API are exposed for end user to query spans. We also found one single cluster is not horizontally scalable, so we have a ring-based discovery solution. New clusters can be added to the ring very easily, and spans will be routed based on service name. We have a global index table, which allow the query to skip shards which don't have target data. Okay, this is our schema design. We have one big index table, and it basically just holds metadata, like the service name, host name, cluster, something like this. And we have two data table. The first one is traces table. It only holds few hours raw data. And we have the samples table. The samples data will hold a few weeks data, okay, of the sample. Other tables like the service operations and traces service table, they are only used to help some queries. And examples from metrics, they are saved in the sample trace ID table so that they can be picked up in later sampling process.
So before I talk about sampling, right, like I want to call out one fact. If you had noticed in the last final configuration that we landed on, you won't see the tail sampling processor here. And one of the reasons is that like tail sampling on the OpenTelemetry collector works only if you are balancing traffic or routing traffic for the entire trace into a single collector, which means that regardless of if your calls moved from one region to another, you need to collocate all of them into, for a given trace ID into a single collector. And this is something that is very undesirable for us because we don't want the tracing, the span traffic to move across regions at any cost. So to avoid that, we went into a true tail sampling based design, which actually can do it at rest instead of doing it on the collector. So that being said, sampling. One of the things that we always need to ask ourselves is every trace useful? And how can we keep getting more and more efficient on the platform, especially on the storage side? So that being said, like this is a very interesting graphic that Riesli came up with, where the entire view of traces can be categorized into everything that succeeded, everything that failed, everything that had an undesirable latency, and then basically traces that might have some special attributes that you are interested in. And probably a sweet spot to retain is take a random sample of everything that passed and then sample everything that has an error, everything that has high latency, and those specific attributes that you're interested in, sample all of them. So that would eliminate the need for more than 95% of the traces that are coming into the platform. So that being said, like with regards to tracing, we take a two-pronged strategy. First, to sample at the head. So we typically recommend the framework to sample at 2% by default, and we employ a parent-based tracer, which means that either the mobile device or the browser, when we have that instrumentation, that would basically decide, okay, before serving the entire request, it would flip a coin, decide if this needs to be sampled or not, and everyone below, thanks to proper trace propagation, will ensure that the entire call chain is being sampled. And on the metric side, we make sure that exemplars are being generated only for those traces that are being sampled. And what we decided to do is go for an exemplar-based tail sampling approach. So when the metric decides that it needs to send an exemplar over, we basically use that as an identifier to ensure that the trace also needs to be sampled and retained longer. So that when you're looking at all your charts, you also have the exemplars there, and each one of those exemplars are clickable for the entirety of the sample trace retention. So we both sample the exemplars that are being generated directly from the instrumentation on the application, also the exemplars that are being generated from the red metrics that are being created by the span metric processor. Along with this, we also generate a 1% random sample to make sure that we have folks have a little bit more of the OK traces for a longer period of time. And we went about doing quite a number of optimizations in the form of PRs to the OpenTelemetry collector. One of the things that we did was red metrics were not being generated for events and exceptions on the span events. There's a merge PR that creates an events underscore total metric for every unique kind of exception, and there's an exemplar for that as well. On the load balancing exporter, we file PRs to make sure that there are different kinds of load balancing algorithms, not just the one by trace ID. Because if you consider span metrics processor as an example, you cannot route by trace ID. If you route by trace ID, every unique kind of service operation and attributes that you have, all of them need to be held in memory on every trace collector. But on the other hand, if you do service plus operation kind routing, then you need to hold metadata only for a given service operation combination on one of the collectors that's receiving the traffic. So some of these improvisations have helped us to make sure that we have, number one, we have optimized usage on the OpenTelemetry collectors, but at the same time, we have an optimized representative sample that we are able to get out of the whole thing. So how does it look like? You have both the tracing collectors that are receiving traces, metric collectors that are receiving the metrics. We write the traces to the tracing ingest, which gets stored on the raw traces table. Metrics go through a metric ingest, a metric aggregator in case we want to do some roll-ups before it goes to storage, and finally it lands on storage. You have the span metric processor that's sitting on its own tier that's generating the red metrics and writing both the metrics and the exemplars that it generated into the metric ingest, and it follows the same path into the metric store. But now you have all the exemplars that are being seen on the metric pipeline being reported into what is called a tail sampler ingest. And these are being stored in its own table in ClickHouse. Now this becomes a feed for a tail sampler job, saying that, okay, get all the, every 5 minutes or every 10 minutes, get all the trace IDs that were part of the exemplars, and make sure that you are moving all those spans from the, or copying all those spans from the raw table to the sample table. So that basically allows us to make sure that for every host, for every latency profile that was seen on your Prometheus histogram or your OpenTelemetry histogram, and for every error that was seen on every host again, you basically collect all those exemplars and make sure that you're retaining them. This is how we can get to that nice Venn diagram that was there to say that, okay, this is what we really care about. So what did we get out of all of this? We have a platform that's much cheaper and easier to operate. The ring-based approach that we have for creating multiple ClickHouse clusters, it makes the operations a lot simpler. It's easier to scale 10 clusters that have 10 shards rather than scaling one cluster that has 100 shards. Head sampling makes sure that we don't have to invest too much on OpenTelemetry collectors, scale them out to a great extent, and make all these decisions. Tail sampling becomes a lot slower if you are doing it against 100%. And we have noticed that with 2%, most of the failure scenarios can always be covered, because it's a 1 in 50 chance that something gets sampled, and we have a very vast call volume that 1 in 50 is very easy to achieve. This also allows us, and this is something that we are building right now, is we don't necessarily need to observe at a per request level. It's easy for us to do both macro and micro level dependency observability. And given that we use OpenTelemetry as the mechanism to bring stuff in, like it's a fairly industry standard tracing platform, both on the ingest with OpenTelemetry and on the query side with Jaeger. And with all these optimizations, they are more geared towards what the company needs. What are the lessons learned? One, observability is a team sport. I think like sometimes we like to say that, oh, if we just use logs, we can derive everything. If we use events or if we can use tracing, that alone is sufficient. We don't really need everything, every pillar to be used. But as you saw during the course of the presentation, we tied metrics and tracing very close to each other, and each of them are being basically used for their strength. And we don't try to stick all the logs into span events. We have a dedicated log platform which is optimized for its own needs, and the 3-click RCA is basically used for navigating through each one of these signals. So like we basically are very particular about finding the right pillar to put a use case on so that it's the cheapest and most efficient way for us to solve the problem. Exemplars, like I mentioned, it's a very good way to extract a representative sample. This is solely off the premise that if an app decides to create a metric, it must in fact be very important, and if there is an exemplar tied to it, we should definitely try to retain it. Numbers matter, like the tuning OpenTelemetry collectors. I think it's a very important thing, because if you don't do it right, it can be very, very expensive. And I think like through this tuning process, like we have managed to cut costs quite a bit. And sometimes the community also comes with the recommended patterns. Unless there is good reason to do otherwise, it's probably wise to stick to prescribed patterns. And the last one is, no one should do 100% sampling on the head. It's very wasteful, and you really don't need it to do effective observability. We have billions of HTTP requests that are served across the various microservices that run inside the company, and if at our scale, 2% in itself is plenty for us to observe issues on the site. And we highly recommend that you look at your use case and see if you can go to lower sample numbers as well, because it's more than sufficient. That being said, I'll stop here, and if there are any questions, we are happy to answer them. Sure.
So in your deployment, what is the size of a route span? Is it something like a page load, or is it an HTTP request, or is it like an entire user session, or like allocating a new trace ID?
That's a good question. I think like we have gone through few permutations. At least on the device side, it was a session, which was not useful, because what ends up happening is that we'll end up having thousands of spans across various kinds of use cases that aren't necessarily connected to each other. So we are going through the process of revising that in a way that we effectively use span linking, so that like the individual call flows are their own traces, but they are all linked together. So that for things that come through the device, like iOS, that's where the trace ID is being generated. But for everything else, it's still the first microservice that's on the front end, which the browser is calling. Eventually, we'll get to a point where browser also does tracing and use span linking for that as well.
Thank you. How do you come to the target of 2%? Was it based on requirements? If I gave you, 100 petabytes of SSDs, would you go for 5%? What was the target, and how did you come up with that goal?
I think we we ramped up very gracefully when we went through the journey. So the first starting point was actually 0.01% where we started, and then ramped 0.11 and then 2. Along the way, we have evaluated to see, okay, what is the percentage of HTTP APIs or request flows where the call volume is not enough for us to observe all requests. Right now, we are at a point where like more than 90% of the use cases are covered with 2%. But for the next level, we don't really want to ramp higher, but we want to have improvised sampling strategies. So one of the things that we are actively evaluating is the usage of adaptive sampling. So the OpenTelemetry SDK has the Jaeger remote sampler, which allows us to basically communicate to the client saying that, okay, this is the sampling percent that you need to use. And the granularity on that is service plus operation, which means that we can say that, okay, for these low volume use cases, those alone go for 100%. So I think like that's the next level of ramp that we are going to do, target the lower ones, which is not going to increase the overall spend, but at the same time, it's going to cover the remainder of the use cases. There isn't, like I said, there isn't a really compelling use case to go higher than maybe 10%.
Thank you for sharing your journey.
Yeah, I can hear you, yeah.
So if I get my math right, 60,000 spans per second comes out to close to 5 billion spans per day. Is that the volume, and what retention do you guys use to store that much spans?
You want to take this one? He'll need the microphone. Sorry. What is the per second value that we are?
Well, right now,
Turn.
well, right now, we have seasonal traffic. So normally it's 2.5 million spans per second, up to 3 million spans per second. Okay, so raw spans will hold for 2 hours, and then sample spans will hold for 2 weeks. Yeah.
Yeah, I think the way that we go for that 2 hours is like, okay, if there's an actual incident that's happening right now, make sure you have as much as you would desire. Beyond that, it's mostly P2, P3, P4 type issues that need to be triaged. For that, as long as you are sampling every error, every kind of error, and some of the OK traces, then you should be good enough for that. Hopefully, we don't have an incident that runs more than 2 hours. That's yeah.
So a year or a year and a half ago, Intuit had done a presentation on how they implemented Restore. And instead of going for 1 or 2% sampling, I think what they had done was at the front end, at the UI itself, do 100% sampling and propagate a signal all the way in a space that sub-services, pick this or pick not. They got a really good insights into the system, but they have to implement a temporary store to store for that 30 seconds or 1 minute,
right.
The whole thing. Have you tried that approach, or what are the cons for that approach?
We have not really tried that. I cannot speak for the pros and cons, but like the general idea is that, okay, even if you take 2% and then compute, say, the red metrics through span metric processor, given that the 2% is a completely randomized sample, for the most part, the shape of the graph is going to be the same, just the values are not going to be the same. So that is good. As long as the shape aligns, you can do things like anomaly detection and whatnot without any extreme loss in fidelity. So, and that observation in itself was like, okay, we don't need to try hard to. And the other thing is that, like I said, right, like we invest heavily on making sure that anything that is warranted to be critical, like 4 golden signals, key business KPIs, and whatnot, we really have double down in making sure that either the end users or the SREs or the framework providers themselves, they go in and do proper metric instrumentation off the bat. So that being said, metrics coming in, lower network volume, easier on storage. You can do months worth of trending for anomaly detection and whatnot. So keep metric use cases as metric use cases. Anything that we can derive for free on trace is great, but that should not be the primary way in which you basically build your observability platform.
I wonder if you have any special treatment for the data values that are tagged into spans, like attributes that might include like user-generated strings or search terms, or is there any issue where the trace span stream ends up being treated as PII that has any kind of special handling?
I think we do have an internal implementation of a PCI PII scrubber. And before the data leaves restricted zones, we scrub it all out before we send it. So that's the only handling that we do to make sure that the data remains compliant. But beyond that, like, we have no special treatment of any attributes that are there on the attributes. We have some standardization that we do in terms of making sure that everything from pod, namespace, region, AZ, all of these are tagged on every span, but beyond that, like, we don't do any, that bare minimal normalization is the only handling of attributes that we do.
I have a quick question.
Sure.
How big is the team that's dedicated?
You asked me the same question last year for my metrics talk, and I'm
I know, just it's a money thing, right?
I'm legally not allowed to answer that question.
Anyone ask another question that's not last week? All right. Thanks, guys.
Thank you so much.